Thank you very much. So my presentation is about spatial autocorrelation. It's a thing that I've explored last year at the CIA during the session about new methods for the use of R in archaeology. I provided a review of the different statistical methods used in archaeology to explore spatial autocorrelation. We've got some here. If you're interested in my presentation and the data and the analysis and the implementations that I reviewed, you can find it on my GitHub. I'm not going to spend so much time talking about this because, of course, he's already there, and it's a well-established technique or series of techniques. Basically, is the property of spatial data to vary their value of certain parameters according to the distance or the geographical space. However, in archaeology, the spatial autocorrelation is largely or exclusively investigated for numerical continuous variables, not for categorical variables. There is a well-established statistics called joint count statistics, which explores spatial autocorrelation, global spatial autocorrelation for categorical variables, namely how if in this case it's called BB or WW because the idea is that you have black cells and white cells, and if black cells are closer to each other than expected, you have autocorrelation. If white cells are closer to each other than expected, you've got autocorrelation of white cells. If black and white cells, as you can see in the third equation, are closer to each other than expected, you have negative autocorrelation or no autocorrelation in this case. There are some assumptions. The first assumption is that, of course, the independence of black and white, but of course this is what we're exploring. And X is a realization of a random variable of a Bernoulli distribution. So again, as we said, black or white. And the other assumption is that they are X with I and X with J are equiprobable, which is not always the case. Since both the statistics BB, WW, and BW demonstrate asymptotic normal distribution, their significance can be explored using the Z-test. Pretty simple. The reason, as we will see later on, the reason implementation of this test in SPDEP, a package, an R package for the analysis of spatial dependencies. So it's not particularly innovative. As far as I know, it's never been applied in archaeology, and the reason is, as far as I'm concerned, that there's no solid method to assess the local autocorrelation, which is, okay, this is a summatory, so we have the overall global autocorrelation of black and white cells, or whatever you want to call them, but you don't have a local indicator of spatial autocorrelation, which they exist for numerical variable. They're called LISA, local indicators of spatial association, but they didn't exist for categorical data until quite recently. In 2003, Barry Boots explored the possibility of developing local indicator for categorical data, and he called them LICD. The problem with categorical data is that local autocorrelation, because we are talking about binomial values, requires two measurements, not only one. One is at least two. One is the measurement of composition, and the second is a measurement of configuration. We will see it later. As far as composition is concerned, so boots, I'm going to go through the method really rapidly. So in order to explain how I implemented it for archaeological data and how it can be used in archaeological data. I'll try to be as quick as I can on this. So Boots implements a moving window. As you can see, is each cell, each window is at least 30 regions. This is based on tests in management. And in these moving windows, of course, the realization of the autocorrelation, so the contiguity between, or the proximity between, or the occurrence of black cells within this moving window follows the binomial probability mass distribution. So it's pretty standard as a method to assess the probability of having black cells or white cells within this moving window. These moving windows is centered on each cell, and so you have the autocorrelation of the individual cell compared to the other cells within the window. This is only related to the composition, so the probability of having a certain number of cells within a given moving window centered on each cell. The probability, the null hypothesis here is, first of all, there is an assumption on no global autocorrelation. So in the whole study area, in the whole region of investigation, the data are not autocorrelated. This is the assumption. And the other assumption is, like, the other important thing to remember is that the null hypothesis is conditional in this case. That's why we need an additional parameter, which is the configuration. So the null hypothesis, I need to read it because of course it's quite complicated. So given the number of black cells composition in a local space, so the window, the value of configuration of LICD is not significantly different from what would be expected if the black cells were located by chance in the local space. So it's not only a matter of the number of cells you've got, or black cells you've got within the window, but also how they cluster. Therefore, the analysis of local configuration is required. So how close these black cells or white cells are within the window. And this is investigating using the same binomial mass equation, mass probability equation, for joins and not for values. And then we use like this summatory that analyzes the probability of having clumps, so clusters, and their size, and then sums them all up for the area of the window. As you can see, this method is really sophisticated, fairly sophisticated, but really complicated, especially if we're not dealing with regular lattice. And this is a thing that we need to consider later on. So another aspect, I'll go very fast because I've already been given a warning. Another thing is that in a later paper, Boots acknowledges that one measurement of local configuration is not enough. And based on existing studies, especially in image processing, he defines 5 different alternative ways of analyzing spatial configurations. Most of which, so some are based on the analysis of join counts, some are based on the analysis of patches, their size, their distribution in the space within the moving window, and so on. In our case, we're going to focus later on, so in 1 minute probably, on this, the number of black and white joins, which is nothing more than a local version of the join count statistics we've seen at the beginning. So, as I said, this method was developed for for a regular lattice. But Booth says that there's no theoretical limitation in applying it to irregular lattice, like, for instance, the one you can see that is more common in archaeological research, for instance, landscape archaeology, the one you can see here at the bottom. Roger Bivand and some collaborators have adapted the methodology that Booth has developed for irregular lattices, and instead of using a moving window, which was not very appropriate apparently for non-regular lattice, then if you want we can discuss later on why, he used sets of neighbors calculated as we will see in different ways. Now I'm going to present really briefly my application to archaeological dataset and explain why it can be useful, Bivand's adaptation of Booth's methods, of Booth's LICD for archaeological purposes, and what the limitations are. Joint count statistics, as I said before, is implemented in this SPDAP package. LICD is not implemented yet, but it's still work in progress. We're still working on it. So, as archaeological example of the application of LICD, I used historic landscape characterization. This is a qualitative but formalized methods to characterize the landscape, so discriminate the landscape into chronologically and spatially homogeneous units. So create categories or landscape types that we can use to analyze spatial and temporal relationship between these categories or landscape types. The case study specific that I used is the historic landscape characterization that we've prepared in Newcastle for an area in southern Turkey. And in particular, I analyzed, as you can see, there are a lot of different categories, and these are only the broad types, not the individual character types. So I've used as an example the suitability to change, which is I queried those polygons that change between the 1970s and the 2010s characterization, and which are the black areas against the those polygons, those areas that didn't change between the 1970s and 2010s. And I've analyzed whether there is a spatial autocorrelation between these character types that changed over time, and whether this autocorrelation is clustered in specific area of the of our case study. One problem that I want describe in depth here is the problem of neighbors. Bivand uses contiguity neighbors, these ones, because it's more is closer to the concept of joint counts provided by the configuration analysis suggested by Booth. In our case, I don't think it's suitable, because contiguity neighbors assumes that contiguity neighbors assume that there is each area is distinctive, whereas in archaeological dataset like this, the boundaries might be conventional, might not be real. So it might be that we are analyzing the autocorrelation between two areas that in fact are the same area. So I decided to use key nearest neighbors, and in this case I set key to 8, because the average number of neighbors for continuity neighbors was nearly 6. So I wanted to go over the average number of neighbors. This is the joint count statistics. As you can see, with continuity neighbors, the WW are significantly autocorrelated and black BB are not. BB are the black areas. Whereas for the key nearest neighbor is the opposite. So first, interesting problematic results. And this is the LICD, the application. I plot as black the areas that are significantly autocorrelated. So there are significant clusters, significant composition, and there are significant black and black and white joints. Whereas the red areas are outliers, so significant outliers, non-clustered, and significant black and white joints. As you can see, for key nearest neighbor, as we expected, the number of autocorrelated polygons is much higher because the number of neighbors is much higher and is consistent across the study area. And the number of outliers is pretty much the same and is very low as we expected. Whereas for contiguity neighbors, the number of autocorrelated data is fairly low. So let me see if I can have to say something about that. Otherwise, we go to a conclusion. The main problem here, like the problems are four, and these are problems that we are trying to address, like 2 or 3 problems, and one is the implementation. Number one is that we need to provide an agile method to estimate significant statistical significance. At the minute, we can easily analyze statistical significance for composition, but not from configuration, for different statistical issues related to the fact that we're using a set of neighbors rather than a window, and we're using an irregular lattice. The second problem is the problem of neighbors, as I pointed out before. Logically, theoretically, the use of key nearest neighbor for archaeological purposes is more appropriate, but we need to make, and I haven't had the time to do that yet, some tests to assess the mathematical implications of using key nearest neighbors over contiguous neighbors. The third aspect is that the next step for me is to apply it to archaeological regular grids, which is much more straightforward. That's why I didn't explore it here. But archaeological grids are very common in excavation, for excavation intra-site and for landscape surveys. So it might be really useful there as well. And then, as I said before, we are developing a tool that will be integrating to SPDAT package for LICD. That won't be very soon, but we're still exploring some of the issues that I presented here. And I wish, and I'd be happy if you had some feedbacks or some questions or some doubts, so they can help us exploring these possibilities. Thank you very much.